Hello, today's lesson is about understanding. Oh, where's my pen? Understanding. Okay. Oh, yeah. Okay. Is about understanding standing numbers. Understanding numbers. All right, for pre-algebra. All right, so here we go. Real numbers. What are real numbers? So real numbers are any number or any set of numbers, that include or which includes both rational and irrational numbers. Irrational numbers. A set of numbers which includes both rational and irrational numbers. Is that like saying numbers twice? Okay. So it's any set of numbers that they could be rational numbers or they could be irrational numbers, but if they're either or, they are considered a real number. So what is rational? What are rational numbers? If you think of the word rational, we use it when we describe people sometimes. And rational means that they're not being reasonable, not easy to work with or easy to, easy to work with or easy to figure out, right? So an irrational number can be a decimal that never ends. Numbers that never end and go on forever and ever and ever are irrational, right? They have complexities to them, right? They keep going on and on and on and on. And if we needed to use all those numbers, there's no pattern there that we see. So they're irrational numbers. And they have no repetition, right? A number that's not repeating. So repetition means that it's 0.3333333. That's a rational number. Irrational numbers means that the numbers go on and on and on and on and on. It's like 3 or 0.326464231789, right? There's no rationale to why those numbers are the way that they are. An example of this could be, I think someone mentioned it today, is pi, right? Pi is that very famous number that a lot of us, we know this number. It's 3.14. I'll put it on my calculator, be patient. It's 3.141592653589793. So it's very irrational. It goes on and on and on, and it will continue to go on and on and on forever because it's never going to repeat a pattern. There's no pattern being repeated here. So pi is an irrational number. The square root of 3 is an irrational number. If you put the square root of 3 into your calculator, just to verify. Can I please get this on? Sorry, I had to pause the video. There's an announcement. If you put the square root of 3 into your calculator, you'll get a number like 1.732050807586877, and it'll keep going on and forever, and it has no pattern, no repetition. Numbers aren't repeating in there, not consistently repeating, right? There's a couple of 8s, a couple of 7s, but there's no pattern involved in the numbers. They just keep going on and on forever, making them very irrational, not easy to work with. Other numbers like 5, square root of 5, or 41, the square root of 41, not 41 itself, but numbers that are complex in their usage. Okay, then we have, so if those are irrational numbers, then the opposite is true for rational numbers. Rational numbers should be numbers that are easy to work with, right? Rational numbers are all fractions or numbers that can be written as a fraction, where a and b are integers. So a and b can be integers. And we remember what integers were, right? We started off our unit talking about integers. Integers are any number on the number line. They can be positive or negative. 0, 1, 2, 3, 4, 5, or -1, -2, -3, -4, and -5. So they can be placed on a number line. Those are integers. So rational numbers can be fractions or can be written as decimals that can be written as fractions. And the a and b are both integers. So again, I said the opposite is true for rational numbers. They are decimals that end. They use the word terminate in math, but you can use the word end or terminate, I guess, so that you know the word. I will put it here. End or terminate. I'm going to put it up here too. End or terminate. Okay, or have a pattern, or they repeat. They have repetition. Okay? They have some sort of repetition to make it easy for us to understand why it's repeating over and over again. They are rational. We can work with them, right? Fractions like, examples would be like 2/3, or 4, or the square root of 4, or, I don't know, 0. Easy to work with, rational. 25/5. The square root of 81, right? 10. Numbers that we can work with. Numbers that have an ending and some kind of repetition that make it easy for us to deal with. Those are rational numbers. All right. Let's classify what a rational number can be. So we have this big category called rational numbers, and then those can include these 3 categories. So they can include integers, and we just said what integers were. They are any number on the number line, right? They can include both positive and negative. So we have, sorry, I lost something. Okay. Integers can be -5, -4, -3, -2, -1, 0, 1, 2, 3, etc., right? They go both ways on the number line. Okay? All right, and then whole numbers. Whole numbers are numbers that that you can use and that describe the value of something, right? So you can have a value that is 1, 2, 3, 4. You can't have a value that is negative, right? Because there's no value in negative. That means it's being taken away, right? So whole numbers would be numbers that, or think of it this way, numbers that make you whole, not numbers that take away from you, but numbers that make you whole. And so they can only be positive. Whole numbers can include 0 too. So only positive. Whole numbers are only positive. They make you whole. If you think about that in terms of money, right? If it's negative, that means it doesn't make you whole. It's taking away from you and you have less of it. But if I make you whole, right, I give you something, I make you whole and provide something to you. All right, and then lastly, I'm gonna put these in parentheses, only positive. And zero is neither negative nor positive. It's just a whole number, right? You can be whole and not have anything. Natural numbers. So that falls into what a natural number is. A natural number can't be 0. It's all positive numbers, not including 0, because 0 is not natural. You can have nothing of something, or it's not a number that's made based on value. So it's a natural number whole numbers, natural numbers can be whole numbers, and whole numbers can be whole numbers can be natural numbers, or natural numbers can't be whole numbers. All right. I said it backwards. Okay, so let's organize this. The relationship between sets are frequently shown through this diagram. I know somebody mentioned that some of you might have seen this in computer science. They use it to explain relationships between things, I'm assuming with some kind of coding process. In math, we have a big category, so we're going to say the big box. This big box here, I don't want to, maybe I can highlight it. This box here represents whole number or real numbers, all real numbers, right? But then we have numbers that are complex or not easy to work with. We know those are irrational numbers, right? Irrational. And then we have which irrational numbers are real numbers. They're just irrational. They're in a category on their own. They're grouped by themselves. And then we have this outer circle, right? So we have rational numbers are numbers that are easy to work with, rational. And rational numbers can include integers, both positive and negative integers. Integers can include, yep, you guessed it, whole numbers. Integers include whole numbers. And whole numbers include natural numbers. Not all numbers can be natural, but natural numbers can be whole numbers, and whole numbers can be integers, and integers can be rational, but they are all numbers. All right, let's keep it going. Let's do a couple of practice, or I'll do these examples and practice ones with you. Here we go. So let's look at, you're going to name all sets to which each number belongs. So negative 47. Negative 47 is definitely an integer, or we could start with the big box. It's an integer. We can identify it as an integer because whole numbers aren't negative and natural numbers aren't negative. It's definitely an integer because it's negative, so we'll say it's an integer. We know it's a real number because all numbers are real numbers. And we can say that it's a rational number, right? Good. Not too bad, right? Pretty easy. All right, let's look at number 2. If you're not sure what this is or where it would fit, we know that it's definitely rational because rational numbers include fractions, right? It's rational. And we know it's real. If you're not sure if it would be irrational, maybe put it in a calculator and see if it goes on and on and on forever. And if it does, it would be irrational instead of rational. But it does end. I think the number is 2. It would be 2 and 3, 7, something like that. I think it ends. All right, so we have an absolute value of 9, which is just 9. And we know 9 can be a real number. Ooh, 9 can be a lot of things. It can be a rational number. We know 9 can be an integer because it's on the number line. You know, it can be a whole number and a natural number because it's positive. Well, I'm going to put this up here because I ran out of space. Natural. All right, cool. So we're going to keep going. 23. If I put 23 into my calculator, I think it goes on and on and on and on forever. And so instead of putting that, I know that it's irrational. Ooh, I can't spell apparently. Irrational. And then I know that all irrational numbers can still be real numbers. Okay? All right. I can see here, can this be written as a fraction? I think it can. If you wanted to make it a fraction, it's 1, and we would move the decimal, 1, 2, 3. It would be 25 over 16, which means that it can be written as a fraction, so it's a rational number. It doesn't end forever. It doesn't go on forever, and it could be real. All numbers are real numbers. We know that for sure, so we can actually put real in all of them. So zero is definitely a real number. We know 0 can be a rational number. We know that 0 can be an integer because it's on the number line. And we know that it can be a whole number. All right. I'm always going to start off with real because all numbers are real numbers. Right? Real. The square root of 64 is 8, but there's a negative sign out here. So this is -8, and -8 is definitely a real number. It's a rational number because it's easy to work with. It is a integer because it's on the number line. And that's it. It can't be a whole number because whole numbers are only positive, and it can't be a natural number because natural numbers are everything including, or all positive excluding 0. All right, number 8, if we wrote it as a fraction, and it's repeating, there's a repeating line up there, so we know that it should be over 9. 9 has repeating numbers, and if we move the decimal, so 1, 2, 3, maybe 9, 1, 2, 3, and it's negative. So it's a real number, and we wrote it, so it's rational because it's repeating. That means 1, 2, 3 repeats over and over. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. All right. -24 over 6 means that it is 4, sorry. It's -4, and -4 is a real number, we know. It's a rational. It's a integer. But it can't be a whole number, and it can't be a natural number. All right, last couple, and we have the cube root of 8 is 2, and we know that 2 is real, it's rational, it's an integer, it's on the number line, it's natural, and it's a whole number. Good. All right, easy, easy, easy. We're going to look over here and classify them. We're going to place the letter of the values to the left in the smallest set that contains the value. So we have the square root of 50. I can already tell you that that's going to be irrational because it's under a radical symbol. So we know that A is irrational. B is rational for sure because it ends. Let's see, C, but it's rational. It's an integer. It has a lot of digits after, so I wouldn't put it in integer. Let's see, 8 can be, or a C, that's a natural number. We know that natural fits into whole, integer, rational, and real. D is -11. We know that D is an integer, but it can't be a whole number or a natural number. So it would go upward and out, right? This C would go all the way up and out into real numbers. E would be a rational number because it can be written as a fraction. F is pi. We know pi is irrational. G has a repeating pattern, so I know that it's definitely rational. H has a square root. 196 can be squared. 196, I think this is 12, 13, 14. The square root of 196 is, oh boy, I'm gonna look really quick. Sorry, I'm trying to go quickly for you. 196, the square root, 14. And 14 is a natural number, h. So h is natural. 0 under a radical symbol is definitely a whole number, right? Because it's 0. J, absolute value of 34 is 34, but there's a negative symbol out here. So we know that J is an integer. K is a fraction. It would be written as 1 over 3. So we know that it's rational K. It can't be an integer because it's a fraction. And fractions can fit on a number line, but in a smaller set. 27 over 9 is 3, and 3 is a natural number, so L goes there. And M, if we wrote M out, that would be a decimal, and that would be rational. I don't think it could be an integer, it would be really tiny. And then the square root of 4 is 2, but then there's a negative sign on the outside, so it would be -2, and -2 is an integer. Well, all right. Good. Hopefully that made sense. If not, we can talk about it. Come and ask me questions. I'll see you in the next lesson.